Hi guys, welcome to another video. This one will be a very different video and a very fun one. We'll try to create the whole reconciliation algorithm or our own. Okay, so if you guys don't know what a reconciliation algorithm does, basically in React, whenever there's a state change or a UI change, React tells Fiber that these are the changes that happen. Now, how it tells with the help of this algorithm, reconciliation. Today we'll try to create a very small version of it, very a cute version of it, right? Okay, so by the way, React stores the component data in kind of a tree like structure. I have created something like this. Okay, so yeah, I'll just position my camera here. Yeah, so what happens is it creates a type and then its children components. Children components also have a type and then props and then type and something like that. Now I have created two nodes right now here. Okay, old node and a new node, an updated node. Okay, and we'll try to create the function that will help us find the differentiation between the two. Okay, let's try. Reconcile, we'll add old tree and new tree in the params. Okay, now we'll store all the changes in the array called patches. Okay, so what is the one big thing that can happen beforehand? So the change that comes into my mind is if the whole component is now changed. For example, here we have div, right? It is changed. It is changed to something of a p tag or something. Just saying. So how it can happen is basically owner dot type is not equals to new tree dot type, and we're gonna add it, we're gonna push it, we're gonna do something like this, we're gonna say this is remove, and we're gonna write our prompts to be our new tree. Okay, and also we're gonna return our patches array. Okay, this is the first big change that comes into my mind, right? The whole component is now changed. Okay, what will be the what are rest of the changes that comes into mind? The first one is a change of prop. For example, right now we have hello tag and here we have hello react. So this is the change. Okay, another change is an addition. Another could be, for example, a removal if I remove it here. Okay, so these are the kind of changes that comes into my mind. So I'll just write it down here. There will be an update of prop, then will be addition of component, removal of component. These are the things that comes into mind right now. Okay, now we have to check it for our child as well. And how are we gonna traverse it? With the help of recursion. Why recursion? Because it is much simpler that way, and because our child component can also have many child components, so using recursion we can actually get what we are trying to achieve. Okay, we got that. Now before we do our recursion, first let's compare the upper part, the parents tree, right? So we can actually calculate the number of children, the max number of children, by the way. So it will be, for example, old tree dot children dot length, and new tree dot children dot length 0. We're gonna for length equals 0, less than max, I plus plus. Now we're gonna check for the old child and the new child. Okay, so old child will be old tree. Okay, dot children of I, for example this. And similarly there will be a new child. New child will be new child, sorry, new tree dot children of I, like that. Sorry, yeah. Now if a child, if an old child is not present in the new component, what does that mean? That means there is an addition. For example, button is not here, right? That means there is an addition. If not all child, that means patches dot push, okay, type addition, sorry, node new child, and we're gonna continue it because we don't want the rest of the things. Now if there is no new child, what does that mean? That means we are removing that component, removing or deletion, and we're gonna add the, sorry, next one I, we're gonna continue it. Now we have added, and okay, we also need to do one more thing. We need to check for the change in props. Okay, we have to check the change of props, but before we do that, we'll just do our main recursion part. Reconcile old child and new child, and if there are child patches dot length is greater than 0, what does that mean? That means we are pushing dot type, there is a child index si and props as, sorry, patches as child patches. Okay, we need to do one more thing. We need to check and compare our props. We need to check and compare our props. So what would be the best way to compare these two props? Okay, there can be many different things, but one of the best and very nice and cute little trick that I have is to just stringify it and compare it. Old tree dot props, right? If it's not, sorry, not equals to json dot stringify new tree dot props, if something like that happens, that means there is a change in props. Type update prop, sorry, and we have to add the props as new tree dot props. Okay, this is how our sorry, our algorithm is. Okay, let's just console it. Okay, we'll check if there is any other issue. We'll check it. New node. Okay, sorry, open the terminal. Node reconciliation.js. Okay, we have an error. Okay, where is the error? Where is the error? Okay, defined. Okay, we are getting an. Oh, sorry. I forgot to return. I'll patch this array. And now, okay, we got it. We got the child component. Okay, there is a change in child component. A better way to actually log this would be if I again stringify it. Let's stringify our console as well. Oh, oh no, do not. Yeah, so as we can see, there is an update of prop and there is an addition of a button click. Wow, so our reconciliation actually works, and I hope you guys liked it. We tried something new, we made something new, and I know this is not exactly how it works, but the idea is this. The basic idea is something like this. I hope you guys learned something. Thank you for watching. Like, share, and subscribe. Bye bye.